screen? I'm on the screen. Okay, I'm starting a little late. Let's see. Is that the one I opened last time? Or is that the one I opened last time? Or is this the one I opened? Or is that the one I opened? I'll try that one. But you know what? I don't like doing it in this. Okay, where did it go? There it is. I'm going to try to open it with that. Because I found that it seems like you can write on it. Okay, first of all, any questions anybody has? Like any of the, I'm going to try my best to start loading some of the final problems on today. I can't promise I'll have it completely done by today. And then I'll start sending those grades back out every time. Like 2-3 times a week I'll send those out. Okay. Should I do composites and then go back? I'll do composites and then go back. What does that mean? Okay, so composites for second moment of inertia or second moment of the area is a little bit weird compared to other stuff. So what I'm going to do is start a problem, and see, that one's not a good one because the centroid is, you know, right where it's at. Let me just pick one here. That one right there. That's a determine the moment of inertia. That's a good one right there. Let's see. I don't know if I'm able to do that one, but I probably could do. I could do the I and not worry about the X. So I think that's what I'll do. First, see if that software still runs. Okay, start a new one. Add a page. Now, second thing I need to do, go back to here. I'm going to zoom that in and grab the image. And I'm going to drop it right there. So the first thing, pen, here we go. Most of the time, they want you, or it is proper, let's say, or there are reasons that you want to find the I, say, YY, or whatever, or XX, it doesn't matter, about the centroid of the object, which in this case, the object is that thing. So let's look back at the book for 2 seconds. Oh, well, okay, so here. I had it shrunk too big. So if you look, let's just glance at any one of these. Is there a 3? No, there's not. There's this one, and let's just look at this one. So, does he want both of them? Is he trying to find both? Remember the moments that are shared? Oh, he is trying to find both. He's trying to find both. I don't think I want to find both, if it's okay with you. So one of the things you'll notice, these are both rectangular sections. So what I'm going to do is I'm going to label this one 1 and label this one 2. Now I know for rectangle sections, because we had that last time, if you had a base and you had a height and you're looking to find the I wonder if I should leave that with just one. it's 1/12, or usually base times height over the third over 12. So, and actually, glance back at the book. So let's take he's written it, in rectangles A and D. So he's written here. So what you see is, I think I can use this button. Yeah. So what you see, I'm just going to focus on this. Of course, I think I wrote my subscript wrong. But anyway, we'll look at that in a second. So he took A or D, imagine either one, and you find the centroid about its own location, or you find the eye about the centroid of that particular rectangle. It's 1/12 the base, and the base is that 100, and then the height to the third, and then we'll start here. So what we're going to do is stair step through here. So we're going to start here, go back here, and I think I should have written X, because I just want to find the X. And what this is, imagine in some books they'll write it this way. They'll write a section XX, and they'll take the centroid. But in that, I mean, take the second moment of the area. But then that is related to the Y, because if you look at it, but we're not integrating right here. We're just using the equation. So, oh shoot. No, that's okay. So, I get confused about hitting these buttons on the top or hitting the Alt key. So, we got section 1. So what we're going to do is make a little table. I'm going to make a table with A, X bar. I'm going to go ahead and do Y bar, or I'm going to do X bar, even though it's kind of stupid. And then I'll do X bar area, just for the sake of argument, and then Y bar area. So I probably won't use this, and then won't use that. Then I'm going to find the I of each section about its own centroid. Okay, so I only have 2 sections. I have 1 and I have 2. Okay, you'll see why I'm making this table. Although I put too many entries in it, you'll see why I'm making it in a minute. Okay, and I might be too lazy to do the other one. But anyway, the area, 30 by 150. That's for 1. 30 by 150. Oh, and the other's 30 by 150 too. So if I wanted to erase and put the actual value in there, 3 times 15, that's 45 with 2 zeros. So the actual area becomes 45 with 2 zeros. Here's why what I was talking about is pretty dumb. Okay, so if this is the X, then this is 0, and that's 0, and that's 0, and that's 0. But that doesn't matter. So what we're going to do right now is measure from the bottom, because he's telling us kind of to do that. Give me the Y bar about the bottom. Well, okay, so here we go. The Y bar of 1 is I'm going to move up 30, and then half of that, which is 30 and 75, that's 105, I think. So that's 105 for the first one. The second one is just halfway up, and its centroid is right here. So that's 15. Oh, shoot. Well, let me use my cell phone. I don't think I'm going to be too complicated here. So I don't even need, okay, so 4,500 times 105. Oh gosh. Okay, let me see. 4, 7, 2, 500. And 4,500 times 15. 6, 7, 500. Now, add this up, and I get 9,000. Add this one up, and I get that plus 4, 7, 2, 500. I get 5,400, or 540,000. So if I want to know y bar, it's equal to the sum of the y bar areas of the little i's, which there's only 2 of them. I equal 1 to 2. Sum I equal 1 to 2 of the areas. So that ends up being this number divided by that number. 9,000. Around 60. Actually, exactly 60. So we'll need that in a second. Okay.
Get the 60 again. What did you do to get the 60?
I took this 540,000 divided by 9,000. So, yeah, I could go in and do an extra step there here. Here. That's not a touch screen. 540 divided by 9,000, and that was 60. Now, what I got to do is now that I've found the centroid, that's something I'm going to hold in the back of my mind and say, I'm going to need that because I think the problem statement, oh shoot, the problem statement's not there. Okay. Problem statement said, determine the moment of inertia of the cross-sectional area of the TV with respect to the passing through the centroid of the cross-section. So he has drawn this line that is a horizontal line and implying that the centroid sits right here. And so we needed to find how far I needed to go. So in fact, I need to go 60 up there. Now I'm going to focus on these terms. Okay, now this is going to be a lot of big numbers. So you know what I'm going to do? I'm going to slide the thing to the right if it'll let me. And I'm going to do them for section 1 and section 2. And then I'm going to put the numbers in there. So it's 1/12 base times height to the third. In this case, the base was, shoot, I forgot. The base was 30. So the base of this first one's 30. The height's 150. So it's 30. Base is 30. Height's 150 cubed over 12. Section 2 is different. The base and the height are swapped. So the base is 150, if you notice. Here's your base, and your height's 30. So I get that over. So your height's 30. And so that's the reason I want to do these separate, because these are big numbers, and they can be annoyingly big. Not in a bad way. 150 times 150 times 150 times 30 divided by 12. Okay, so this is how annoying it can be. 8, 4, 3, 7, 500. That's the bigger of the two. If you look in here, it's 30 times 30 times 30 times 150 divided by 12. 337, 500. So now I need to copy these to put them in this thing here. So 8, 4, 3, 7, 500. And then I'll copy the other one, 3, 3, 7, 500. I just didn't want all this junk to end up in this box and be confusing. I just want to do it up here and then copy it into the box. Now the next thing that's quite interesting is I'm going to do two columns that are going to help with what's called the parallel axis theorem. Okay, now what you need to do there, okay, let's go back and look and see. Oh, it seems I'd bounce around everywhere. Okay, so here's the page. Notice what he did here. Well, anyway, here. Notice what he did right here. He took the value. I can erase this. Maybe. Okay, that's good. So what he did, give me a second. He took, if you notice, he took this at its own centroid. Let's just say A. I mean, A and D are the same. So we're going to just say we're focusing on A. So 1/12 the base, like we talked about before, and the height. But this is the second moment of area about that point, that little dot there. But what he wants to do is now he wants to move it off somewhere. Now, it's kind of like that concept. Remember, if you look back at a lecture, I did the block, and if I found the second moment of area here, I got 1/12 base times height to the third. If I did it down here, it was 1/3 base times height to the third. So wherever you move it to, it's going to be different. This will be the largest one. I'm sorry, that'll be the smallest one. Said that back. Let me repeat myself. The second moment of the area about its own centroid is going to be the smallest one. Because if you move it away, no matter whether you're moving it up or down, that D becomes squared. So if it's a minus, it's still the same. So this adds to it. Think of it like this. Take an object and I spin it about this. How much resistance to spin would it take versus taking that object and then welding a little string or some sort of thing and now spinning about it? It would be hard to spin it up here because you're further away from it. It would look the same as if you moved on this side that distance and you spun it here. So essentially that's what this is. Here, so what we're going to do is we've got to address the D, and then the A's already been addressed. So if you look at our table, you'll find the A already sat here. So I need to address the D. And I'm going to address the D, and then I'm going to make a column that says A dy squared. Okay, so if you look back, how far did he move it? He moved it 200 millimeters. Why did he move it 200? Well, let's see. Wait a minute. Where is his? I'm looking at all his dimensions. What the heck is this dimension from here to here? Is it up there? Oh, it is. That is weird. Okay. So this is 100. It's not listed on the page below. So, okay, let's look at this. This is 100. Now.
Wait, hang on, scroll up.
Did I have that wrong?
Say scroll up a second.
400, 300.
400 minus 100, 300, right? Is that what you're reading out of that?
Yeah.
Because
But also,
dimension looks like it's trying to say right there is 100.
This one at the top?
Right there is
Yeah.
what I think it's trying to call 100.
Yeah. And this being 100, gives you that 300. And so this is the distance he's saying from B all the way up to A. So that's 50 right there, and that's 150 right there. So that's his 200. So he is finding this about that location, or really about this line here. So we're going to do the same, although not the same numbers. We need to find dy. And this is where things get really tricky. Okay, dy is of course different for each one. Okay, so this is the centroid. This is where the centroid is located, this dot here. That's the centroid. Now, this is the location that we found the eye about. How far do I have to move? I have to move to here. Doesn't matter whether it's positive or negative. So, okay, so this one sits from the bottom. Okay, let me get some erasing going here. And it's just a matter about measuring distances here. Okay, so here, I'll even do this. So this height is 60. This height to the centroid of that object, of object number 1, I have to move up 30, and then I have to move up half of 150, so that's 105. So that makes this distance 105 minus 60. What is that, 45? Is that right? I think it is 45. Okay, does that make sense what I just did? Because this is the most comprehensive. It's not hard, but it's confusing. So again, I repeat, I'm finding the eye about this point and the eye about this point. And then I need to move to there and then move to here. So I have to do them individually, kind of separate, so that dy for this one is 45. Does that make sense? Now, the distance from here to there, this distance is 15, and this distance is 60. So 60 take away 10 is 50. Take away 5 is 45? Am I seeing that right? So it's 45 for both of those. Okay, correct me if I'm wrong. Okay, let me zoom in here a little bit. Because what I'm trying to do, trying to move that one down and this one up so that they're both along that line. Okay, again, that's 30, so half of this distance is 15. We found this at 60, so that means 60 minus 15. I think that's 45. 4, 5, yeah, that's 45. So this, it doesn't look to scale, but this is 45 here. Okay. And I think I got 45 here as well, although they don't look the same distance. That's a little bothersome to me. I don't know why I'm bothered by it. I can't find my mouse. What's bothering me is this one, okay? Okay. I move 30, and then I move half of 30, which is 75. So,
half of 150?
half of 150, I'm sorry, is 75. Yeah. And that gets me to here. So I move up 30, then I move up 75. Isn't that 105? And then I need to move back down a certain amount, but that back down is 60. I'm not moving back down 60, but in other words, here, I'll change colors. In other words, this distance plus this distance has to be 105. So what is 105 minus 60? I think that's 45. Yeah. So for really weird reasons, and don't expect that to ever occur, because that's just weird. Because if I would have shortened this 150 down to 100, that probably wouldn't have occurred. But I don't know. Just don't expect that to occur naturally. Okay, so I got 45. Okay, I'm trying to get back to here. Now what I need to do, and these are big numbers. The next thing I'm going to do is big numbers. I have to take the area, multiply it times d squared, and put it in this column. And so this column is going to be big and wide too. Man, I'll just use my cell phone. 4,500. First, I'll take the square. And actually, ironically, it's the same for both. So give me a second. Okay, 45 times 45, that's 45 squared, times 4,500, 9, comma, 112, comma, 500. And believe it or not, I wish I'd have picked a different problem. I didn't know that this was going to occur. So now what I need to do is I need to find this, I xx bar plus a dy squared. So again, I'm sticking with the concept of making myself like an Excel spreadsheet here. Oops. So I take this column, or this number, add it to that number, and put it here. Okay, I still have that number sitting in the calculator here. And then I add 8,437,500. 17,550,000. Now I take this number, which is smaller, and add it to that number, and then put it right there. So 9,112,500 plus 337,500. 9, 4, 5, 0, and then some commas, and then 0, 0, 0. And then I just add them up. Okay, so let's go back to the problem here that he had. Okay, he ended up, and you can see he got large numbers. So he ended up with this for both A and for D. Then what he does, okay, let's see. You scroll down, he's working on rectangle B. And of course I got a bunch of junk in the way here. So when you work on rectangle B, give me a second. B itself, they make you work hard to erase this, don't they? Okay. Okay, so B, rectangle B, another thing is to erase. In his rectangle B here, give me a second. There's probably a setting where I can change that, but rectangle B, it turns out you're already at the centroid. So you don't have to use the parallel axis theorem to move you away from the centroid. So what do? 1/12, of course. Base, which it should be base from here to here. And then height of 100 from here to here. And you get this number. Now, you have this number that's already moved, that because of the parallel axis theorem, you moved it to this point. You have this number, which was at this point as well. So what do? Okay, I'll shrink it down so I can fit them both on the page. So what he does is he says, hey, I've got I got an A and a D, both move the same distance. This one moved this way, this one moved that way. There are two of them. They both have that number. And then what I do is add this to it, and there's your final answer. So the sequence I'm doing does exactly that same thing. It's just now I need to add it this way, and I get the answer there. And again, I'll go back to the calculator. I've got the 9 million still in there, and I get 17,550,000. Gives me 27 e to the 6 millimeters to the 4th. And that's it. We could go find the answer if we wanted to, I guess. Might as well. I didn't even know the problem number. Okay, it was F10-8. It's F10-8. Did I just say that? Now, I just go crazy and go into it. Okay, maybe I can make it go a page at a time. Okay, there you go, right there. So he lays it out for you. He does this first to find where the location of the centroid is. And then what does he do? He just does a summation symbol. He does one of them. And then he moves, that's how he moved that 45. That's his 45 and that's our 45. Both of those are the 45s. This is the other one. And this is, of course, the area. He ends up with the same thing. To me, I like the organization of the table because I can look at it and see everything. And as I'm calculating, I can move from left to right. And for example, if the problem itself asked for the other one, for the other, the IYY, I could just tack more entries onto this table and just run it out here and do those, but I didn't. That's all he asked. So I like the table because, one, the table kind of, up to here, from here to here, this is the place you find your X bar and your Y bar. And then from here on over, now you're into the IXX or the IYY or whichever one you're doing, or both. And then you can do a column with a D, and then I can do a column where I multiply this one times the square of that one. So I can basically fill it out going left to right. Makes it easier for me to see all the operations and find myself a mistake if I found one. And I have a couple more problems, I think, on Blackboard that I did a while back that I was trying to be real meticulous about it. I think one was a C channel and one's an I-beam, in which I did this. This one has the unique thing that, in fact, you have to find your centroid first, and then you're moving everything to your centroid. Maybe next time I'm going to do a streaming one next time, and I'll talk about why you need to do this for mechanics and materials, why you need to move it to centroid. They'll do it the same thing in mechanics and materials, but there's a reason you're moving the IXX or the IYY to the centroid of the object. And it has to do, I can just give you a glance at it. It has to do with the fact that if you do if you slice a beam and you're looking for the internal load, you put on here a moment and you say, okay, and there's a shear, and you're like, okay, this is great, I like that. But how do you put that moment on there? What does the internal load actually look like? And in fact, it looks something like this. If you have a distributed load that looks kind of like so, that actually produces a moment. Well, it turns out that based on, say you had an I-beam that looks like this. If you have that distribution, let's see if I can make it in 3D. Say you had an I-beam, came over, looked like so, came back. Now, maybe a T-beam or something. Let's say you just had that. Oops, sorry. And then you say, I'm going to put on here the force distribution. It turns out, okay, I'm not a great artist. So if you started here, and then you went to a point, so it started decreasing. And it got smaller as you went down. In other words, it did this. Well, if you look at it, this particular force times the area, this would be larger than this, an equivalent height, because there's less area down here. There's less area here than there is here. So in fact, what happens is the load may shift, meaning it may actually, the beam may sit here like this, the load may actually look like this. And you would say, oh, wait a minute, that's not, if you sum the forces in the x direction, that's not equal to 0. But in fact, it is, because this being a pressure or a what's commonly called a stress, it's occupying, this upper part's occupying more area than this lower part. So in fact, yeah, the sum of the forces in the x does equal 0 if you sum them all up. If you go to start doing stuff like that, you'll start seeing things like y squared d area in them. And you're looking at them and you're thinking, oh, geez, okay. And then you come out with this equation where the stress mc over I, and this I shows up. And this is your moment. And the c is the distance from what's called the neutral axis to like wherever on the beam, either the top or the bottom or somewhere, anywhere on here. And so what you find out is this I shows up. So this part shows up, and instead of you integrating it every time, you might want to use composites to find that number. And then the end of the beam, you might have, 12, pounds per foot or something, some sort of moment here. And this, I guess if that's the case, it needs to be in feet as well. So that's why you're finding this. It's not just because it's something fun to do. Okay, wait a minute.